In this video, we're going to talk about the very important special cases sigma equal x and sigma equal x colon angle n. So sigma equal x is the whole life status, so I'm just going to put a WL there for whole life, and sigma equal x colon angle n. I'm going to think of being in the insurance framework. I'm going to call that an EI, endowment insurance. So this is the whole life status or the endowment insurance. These are really important special cases. What makes them important is because they're the two cases that we can relate the present value random variable for the insurance to the present value random variable for the annuity. Namely, we recall this, that y double dot sub sigma for either one of these statuses, y double dot sub sigma is 1 minus a cap z sub sigma over d. And in the continuous framework, we would have y bar sub sigma equals 1 minus cap z bar sub sigma over delta. So those are the relating the present value random variables. A very important special case. This is going to show up all throughout the exam. Okay, so now let's apply this to, or let's look at our situation here where we're talking about premiums. So let's start by assuming that we're in a fully discrete framework. In a fully discrete framework, and let's also assume that our sum insured is a 1. So we're going to insure a 1. Now keep in mind that if you're insuring a 1, that's not going to imply, that does not imply that the premium is going to be 1. The premium is going to be some amount in order to insure a 1, but you're not going to charge a 1 at the beginning of each year in order to pay a benefit eventually of a 1. That's going to be way too expensive. Okay, so let's just start though with a sum insured of a 1. In that case, then the loss at issue present value random variable will be equal to, in a fully discrete framework, it will be equal to a cap z sub sigma, either one of these statuses, minus whatever that premium is, pi times a y double dot sub sigma. Now I'm going to plug in. For y double dot sub sigma, I'm going to plug in this expression 1 minus cap z sub sigma over d, and I'll get, let's do a little arithmetic here, I'll get minus a pi times 1 minus a cap z sub sigma. That's actually all divided by d. Now let's rearrange some terms a little bit. Let's distribute. Let's rearrange some terms. One way and a convenient way to write this would be to distribute the pi, actually to rewrite the one-term expression in the parentheses as a two-term expression, 1 over d, and then minus the cap z over d. Distribute the pi, and then let's collect the cap z sub sigma terms. So when I factor out a cap z sub sigma from here, I'm going to get from this term, I'm going to get a 1. Cap z sub sigma times 1 is this cap z sub sigma. Now, what will be the coefficient of the cap z sub sigma over here? It will actually be a plus. This minus this must be a plus pi over d. So I get plus pi over d. So that will be the coefficient of the cap z sub sigma when I rewrite it this way. And then I still have this extra term of a minus pi times the 1 over d right here. So it'll be minus a pi over d. So that's going to be the expected value. That's going to be just the expression for the loss at issue present value random variable in terms of the cap z. That's very useful to do, and I'll show you why we're leading into that. Let's see. So then the expectation of this present value random variable, loss at issue present value random variable, the expected loss at issue would be, well, what's random here is this cap z. That's the part that's random. So this is just a constant. I'm thinking of pi is a constant, d is a constant. So I get a 1 plus pi over d, two-term expression, 1 plus pi over d times the cap a sub sigma, and then minus, I'm doing a term-by-term expected value minus the pi over d over here. So now it's a matter of, say, if I'm using illustrative life table assumptions, I just go pluck out. Well, that's not entirely true, because if I'm in the endowment insurance status, then I've got some work to do here to calculate the value of that cap A, even if I'm given illustrative life table assumptions. But if I'm in the whole life framework, then I can just go pluck out that value from the illustrative life table. Again, these are the two statuses for which this is true. Now, this will also be a situation where you're going to be calculating the variance. They're going to ask you about variances of these things, of this particular, the variance of the loss at issue present value random variable in these for these statuses. And it's because if you go back to rewriting the present value random variable for the loss at issue this way, then this minus pi over d is a constant, so it's not going to affect the variance at all. I'm just going to leave that off. And then the 1 plus pi over d, which is the coefficient of the random variable cap z here, comes out as a square of that. So I get 1 plus pi over d squared. And now I'm taking the variance of the cap z random variable. Remember, the variance of the cap z, that's the one that we can work with because we have the upper 2 notation with the cap z's. So that's the expectation of the square of cap z, which is an upper 2 cap a sub sigma, and then minus the square of cap a sub sigma. And that's the that would then be the variance. So all I did was take the variance of the cap z. It's the expectation of the square of z or minus the square of the expectation of z, and I use the cap a and the upper 2 cap a notation. So that's going to be our situation, and you're going to be, again, asked to calculate variances in this situation. Now, we start out in a fully discrete framework. What happens if I change that to a fully continuous framework? You won't be doing this in a semi-continuous framework. For instance, if the insurance was continuous and the annuity and the cap y is discrete, you just won't see that sort of stuff. You're not going to be able to work with those sorts of things generally. So you'll either be in a fully continuous or a fully discrete framework. So let's change to a fully continuous framework. How does this change things? Well, now it changes. This becomes a z bar here. This becomes a y bar sub sigma. So now I got the z bar here. This is going to be a 1 minus z bar. That becomes a delta right there. So let's see, how does that flow through? This becomes a z bar. These d's right here become deltas. So bear with me here. That becomes a delta. That becomes an a bar. This becomes a delta. And then I get a 1 plus pi over a delta, and then the cap a, the upper 2 cap a becomes an upper 2 cap a bar, and the cap a there becomes a cap a bar. So I just flow through and move everything, move all the d's to deltas, put bars over the appropriate letters there, and that's how I can handle the fully continuous framework. One last comment is that what if s is not equal to a 1? If s is not equal to a 1, then the expectation of the loss at issue present value random variable, that's just a general notation for the loss at issue, regardless of what the benefits and the premiums are. And so what this would be equal to then would be, if s is not 1, then just factor out the s, and it would be s times whatever this the above expression, corresponding expression would be. And so what I mean by the above expression here is right here. It would just be, you take that expression and multiply it by s. What about the variance? The variance of the loss at issue present value random variable? Well, if it's not a 1, then the variance is, because you're taking a variance, the s value is going to come out squared, so it's going to be an s squared times the above expression. By that one, I mean this one right here. Okay, so if you can do it, if you calculate these values for a unit benefit of 1, unit death benefit of 1, then you can do them for other values just by factoring out an s or factoring out an s squared, whichever one is appropriate.